This unit that we're videotaping covers the problem-solving aspects of Unit 4 and 5, which is the orbital theory, periodicity, Lewis dot structures, chemical bonding, and molecular shape. The questions I'll be working on are coming from the test review set that you have available to you. Throughout the recording, I will periodically stop the recording, allowing me to refresh to a new question that I'll be solving, and then I will resume. As you can see in the first question here, we're being asked to do drawings of the orbitals themselves. I do want to emphasize that the key words that I would like you to lock in on is the idea of orbital diagrams. Orbital diagrams are specific ways of showing where each electron is placed. Typically, we show it as a series of boxes. In the first box, which represents the 1s, get this right if I can. In the first box, it represents the 1s orbital, and that 1s orbital is the one that carries the electrons at the first shell. According to the Pauli exclusion principle, in a given orbital, you cannot have two electrons with the same spin. And so you would draw two arrows inside the 1s box, one up and one down. Now if you take a look, P, which is phosphorus, the atomic number or the number of protons is going to be 15. So the number of electrons is also going to be equal to 15. And in this first box, the first two electrons go in it. Now that's all that the first shell can handle. We now need to go to the second shell, and there the first orbital it fills up is the 2s orbital. And once again, you would create a spin up and a spin down. Now, in the second shell, there's a total of 8 electrons possible. 2 of them in the s, and the rest are in the p orbitals. And so what you would have was you have 3 p orbitals drawn here. All 3 of the p orbitals are going to be 2p, and perhaps we'll make that one the x, 2py, and then 2pz. Now watch how I fill this up. I fill the first with an up spin, the second with an up spin, and the third with the up spin. If I still have more electrons, I double back and begin to fill the bottom area. This is the basis of Hund's rule, which is you fill up the orbitals available before you double back and then fill in the second electron there. Now, if you take a look, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons are accounted for. The total in electrons we need is 15. That must mean we now go to the third shell. And that third shell would be the 3s, and we have to fill it before I move on to the p. Now there's going to be 1, 2, and 3 p orbitals for the third energy level. So that's going to be a 3px, 3py, and 3pz. And each of them will receive an upspin electron. And at that point, we're done, because I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've accounted for all the electrons that are in the phosphorus ground state. So notice the key word here is going to be the orbital diagram. And the orbital diagram is when you account for every electron in each orbital, which represent by these boxes. Now, in this new problem, we're asked to solve for the electron configuration. Again, when you see the word electron configuration, what should come to your mind is the labeling of S's, P's, and D's. And it's asking for the electron configuration first of 10, which is Sn. So 10, or Sn, has an atomic number, sorry about that, 10, which has the atomic number, can't have problems here, 10 has an atomic number of 50. And so we're going to have to account for 50 electrons. Now what's going to happen for electron configuration is we fill them one step at a time. So Sn will have 1s2, then we have 2s2, then we have 2p6. Now typically you disregard the p, x, y, and z, combine them all, and that fills your 2p6. Then where you go with it is you go with the 3s2, and I just use cursive for the s's because I avoid making mistakes in terms of what I interpret things to be. I would have 3 p6. Now I'd go to 4s2. But now if you look at the periodic table, in the fourth row, transitional elements come into play, and the transition elements involve the d orbitals. But the e-d orbitals have less energy in them, so they don't belong at the 4 level, they belong at the 3rd level. So it's going to be 3d10, and then you go back out again to the 4 level to get the p filled out. You then go to the 5s2, and you get the 4d10, and then you finally wind up with the 5p2. So that's going to be the electron configuration for 10. What about magnesium, Mg? Now magnesium here is a +2, which means it has lost its 2 outer electrons. So if we were to construct it for magnesium, electron configuration is 1s2, 2s2, 2p6, and then 3s2. But wait, this is what magnesium would look like, but it's lost these 2 electrons. So you would not include the 3s2s because that's what has been dropped, and instead you would simply end at the 2p6 value. Right, so this is now problem number 3. And the key statement in this problem is the word shorthand electron configuration. That should trigger in you a certain design. Now it's asking you first for ZR, which is going to be zirconium. ZR is a, that's poorly written, sorry, but ZR is a rather extensive number of electrons. There's 40 of them in zirconium. Its atomic number is 40. And so it's going to be very, very difficult and cumbersome to list every single electron, all 40 of them, for zirconium. So instead what we do is we find zirconium on the periodic table. Again, its periodic number is 40. And what you do is you look backwards to the previous noble gas. The previous noble gas is krypton. So we're going to put a bracket around Kr. And it's challenging for me to do those things, getting used to this. So Kr is the noble gas. Now what we do is we list only the electron configuration of the outermost electrons, which would be in this case 5s2 and then 4d2. And so that would be the shorthand electron configuration for zirconium. Now, how about nickel plus 2? So what we do for nickel is, once again, we're going to find the noble gas that shows up before it. And since the atomic number of nickel is 28, we go backwards from there and find that it's argon. So we put the argon right here. And what that says is the electron configuration of argon is already found in there. And now we're going to only deal with the noble gas configuration of the outmost shell. Now when we do that, you would say, right, we're going to have for ourselves 4s2 and then 3d8. But wait a minute, that's not quite right, because nickel exists as an ion and it has lost its two outermost electrons. So when you look over here, you go, right, I'm going to lose the 2 electrons in the s orbital. Therefore, I would write only argon 3d8, since the outermost electrons are the 4s2. Right, here's a problem number 4. And in this case, it's going to be asking us to draw a Lewis dot structure. And it's got to let us know what kind of bonding does this molecule have. Is it ionic or is it covalent? And so let's begin with the idea of writing down the Lewis dot structure for these items. So what happens is Na sodium has a single outside valence electron. Oxygen has 1, 2, 3, 4, 5, 6 electrons on the outside, and the second sodium has this. Now, what's going to happen is, if you look on your electronegativity chart, the difference between sodium and oxygen, that difference in electronegativity is greater than 2. Therefore, this electron is going to be completely given over to the oxygen, and this electron is going to be given over to this oxygen also. By doing so, this becomes a plus ion, this becomes a plus ion because it lost the electron, and this picked up 2 extra amounts, so it's a minus 2. Now, realize that by sodium giving up its outermost electron, its next shell is filled, it's stable. By oxygen picking up these 2 electrons, it now has 8 electrons on the outside, so it's stable. So the way we would draw this is the following. We would say that Na has no more electrons on the outside. I can make the A stick. There we go. It has no more electrons on the outside of the original valence shell. It exists now as a positive ion. Oxygen has 1, 2, 3, 4, 5, 6. It has 8 electrons going around the outside, and it exists as an ion, so Lewis dot structure says we need to bracket it. I'm having problems here. There we go. That's a -2. And then the sodium will appear just like its partner over there. And so, what is the Lewis dot structure? Nothing around sodium, 8 around these oxygen. You identify what the ions are with bracketing, and you would call this type of bonding ionic. And we know it's ionic because if you look up in the chart, electronegativity, the difference between oxygen and sodium is greater than 2. Therefore, that bonding has to be ionic nature. Now, what about CCl4? Well, what happens here is carbon has 1, 2, 3. Carbon has 4 electrons on the outside. If you look under carbon and chlorine on the electronegativity chart, the difference between them is not very great at all. The result is you'll get a sharing situation going. And the way you're going to create that is the chlorine has 1, 2, 3, 4, 5, 6, 7, and the carbon has the 1, so right here we have a covalent bond. If we now do the same thing over here, and over here, and finally down here, that becomes the Lewis dot structure for carbon tetrachloride. And we would call that bond a covalent bond because there is a less than 2 difference in the electronegativity. Now for this one, let's take a look what they're asking us to do. They're going to do a Lewis dot structure. And once we have that Lewis dot structure constructed, we want to know what the geometry or shape is of it. And for that, you're going to need your molecular shape chart that has been provided. We're going to indicate dipoles, which is the direction of a polarity, and determine if the overall molecule is nonpolar or polar. So this is a pretty sizable problem to working through. Let's take a look at it. The notation is not very good because when I import it to my program I lose it. But what this molecule says is it's NH4, it's an ion, it's a +1 ion. This one is CH2O, and those are the two we want to work with. So, in terms of a Lewis dot structure, this is what we would get. We would get nitrogen, and the nitrogen would have 1, 2, 3, 4, 5 here. And what happens is the hydrogen is going to covalently bond because there's a difference that's significant between the two. And so you're going to get a covalent bond there. You're going to get a covalent bond here. And you're going to get a covalent bond here. Now, what happens is one of the hydrogens loses its electron, and that allows this hydrogen to bond there. The overall molecule is a +1 charge. Now, what about this dipole thing? The dipole simply says does one atom have a stronger pull for those shared electrons than the other? In other words, does it have a larger electronegativity? And what you do is you find out where the electrons are being pulled from and have the arrow point to where there's a greater attraction. So what I just drew, that is showing the dipole. It shows that the electron cloud favors the nitrogen area, and that leaves the hydrogen area with fewer electrons hanging around, making it a polar positive region. And so you get it here, and you would finally get it here. One last time, the plus area is where the electrons are being drawn away from, and the arrow points to where the electrons are being drawn to. So that is a more polar negative region near the nitrogen. And so the dipole direction is towards the nitrogen. Now, if you take a look at your geometry chart, you would recognize this as a tetrahedral, and the system is polar. It's polar because you have the uneven balancing of the electrons because the nitrogen is pulling it towards itself more. Now, how about CH2O? We would put carbon in the middle, and if you take a look at the Lewis dot structure, you have 4 electrons around the carbon. You have 1 around the hydrogen, so they're going to share and create a covalent bond. How do I know it's covalent? Why couldn't it be ionic? And the answer is because the difference in electronegativity between the carbon and the hydrogen, which we would look up on the chart, that difference is less than 2. So it's going to more often share the electrons and not have it stripped away. Now, the second hydrogen is going to be doing the same thing down here. So I've got 2, 4, 5, I have 6 electrons around the carbon now. That's not enough. I need 8. And so oxygen is going to double bond with the carbon, allowing for 2, 4, and this one goes away, 2, 4, 6, 8, and I've got 2, 4, 6, 8 around the oxygen. Now, what about our dipoles? What would happen is the electrons from the hydrogen would be pulled towards the carbon because the carbon has a greater electronegativity. The same thing is true here as it pulls the hydrogen its way. Now on this one, oxygen has a greater pull, a greater electronegativity than the carbon, and so the dipole, or the pulling of the electrons, favors the oxygen. Now if you look up on the geometry of this, this is going to be the trigonal, and it's going to be polar. And it's polar because the overall pull is that direction. Right, so here's our new problem. We're supposed to rank a series of atoms, arsenic, bromine, calcium, potassium, cadmium, and we're supposed to rank them in terms of the overall size and the amount of ionization energy. So the ionization energy is the ability to strip away the outermost electron from that atom. Now both the size and the ionization energy depends upon the ZF number. Now to solve for the ZF number, Z is going to equal to the total number of protons minus the number of electrons that are shielding. That's going to give us the amount of pull that exists on the outermost electrons. So I'm going to solve the first two for you. So arsenic, As, the number of protons is equal to 33. Now, if you look closely at the positioning of the arsenic in the periodic table, what you're going to notice is that there are 3 electrons in the p orbital, 2 electrons in the s orbital. Let's take a look at that. The outermost electrons of arsenic has 4s2, 3d10, 4p3. Now I'd like to really encourage you to look closely at what was just written. This is the orbital structure of the outermost shell. Now we want to know how many electrons are shielding. D is at a lower energy level, so those electrons really are part of the core and therefore are part of the shielding that goes on. Now this is more difficult. The s orbital and the p orbital are both in the 4th shell, but the s orbital sits inside or is a lower amount of energy than the p. So the ps2 is also creating shielding, and all of that is being shielded on those 3 electrons in the p. So what we say here is there's a total of 33 protons. Therefore, there's 33 electrons total. 3 of them are in the p. All the rest are below and create shielding. So the number of shielding electrons is 30. So if we now want to calculate the Z or ZF number, it's going to equal 33 minus 30, which is a plus 3. So the ZF number for arsenic is a plus 3. That is how much pull there is on the electrons on the outside. Now how about bromine? Bromine has an atomic number of 35. So bromine, the number of protons equals 35, and the number of electrons that are involved in the shielding, let's take a look. We are still in the fourth shell. There's 4 S2s, 3 D10, and there's 4 P5. So what we again have happening is those are part of the shield. These 5 electrons are in fact the very outside. But notice something. We once again have 30 here, because that's the total number of shielding electrons. So the ZF number is going to be equal to 35 minus 30. Holy cow. Look at that. Bromine has a ZF number of +5. Arsenic has a ZF number of a +3. Now, first things first. Why did the ZF number of bromine go up? We still have the same number of shields going on. And the answer is because I have more protons now. The fact that I have more electrons on the outside is not relevant. The fact that it's 3, 4, or 5 P's. All I care about is the difference. So what I would say is that bromine, because it has a bigger ZF number, the ionization, let's try again, back it up. The size of bromine atom is smaller than the size of arsenic, because the pull on the outside electron is stronger, reducing its radius. When it comes to ionization energy, the difficulty in stripping away an electron, bromine would have a greater ionization energy because it's harder to pull away the outside electron because it's held on stronger, +5, than arsenic is, which is a +3.